Compounds display constant composition. We talked about the difference between mixtures and pure substances. Compounds do not vary in composition. Most of the substances that we run into, the water that comes out of the tap, the bread in the sandwich that you may have had for lunch, the tiles that the floor are made out of, the material that your underwear is made out of. These are not elements, they're compounds. It's very rare to find free atoms in nature. So most of the things we deal with are compounds. And like I already went on and on about, the compound is different from a mixture of elements. If you took carbon and oxygen and hydrogen and just mixed those three elements together, you're not going to have sugar. You're going to have a mixture of three elements. And one of the things about mixtures is that the composition can vary. In a compound, the composition is always the same. Here we've got a balloon full of oxygen and hydrogen mixed together. A mixture of oxygen and hydrogen. Here, the first time I saw this picture, I'm like, what on earth is that, right? It took me a while to figure it out. That is a water balloon in the process of breaking. They caught it right as it was breaking. So you can see kind of the shape that it was in, and it has just started to break, and the latex of the balloon is pulling around to the front, and the water's still suspended there. It's really kind of a cool picture. But that balloon contains a compound of hydrogen and oxygen. Very different. Joseph Proust formally stated the idea that elements combine in fixed proportions, and this is now known as the law of constant composition. All samples of a given compound have the same proportions of their constituent elements. And this does have implications for actual everyday life. Vitamin C is ascorbic acid. The ascorbic acid that you make in the laboratory, synthetically, the ascorbic acid that you would harvest and isolate from something organic like rose hips or something, the composition of those two chemicals is exactly the same. So just because something was made by nature or made in a laboratory doesn't affect its value or whether it's good or bad. The actual molecules are exactly the same. All samples of a given compound have the same composition. If we take a sample of a compound like water, if we take 18 grams of water, and these numbers are just for instance, if we take 18 grams of water and we decompose it, we'll get 16 grams of oxygen, 2 grams of hydrogen. The ratio there is 16 grams of oxygen to 2 grams of hydrogen, a ratio of 8:1. That's true of any sample of pure water. Get the water anywhere, decompose it, the ratio of oxygen mass to hydrogen mass, always the same, always 8:1. So we can do problems with this, and these problems actually are pretty simple, and yet students find them very, very confusing. So try to make this a little as clear as possible. So 2 samples of carbon monoxide obtained from different sources are decomposed into their constituent elements. So we need to recognize 2 samples of carbon monoxide, same compound. It's going to have the same proportion or same ratio of the elements. So one sample produces 4.3 grams of oxygen and 3.2 grams of carbon. The other sample produces 7.5 grams of oxygen and 5.6 grams of carbon. Are these results consistent with the law of constant composition? So what we need to do is see what the ratio of oxygen to carbon is for both of them and see if it's the same. So for sample, let's just call the first one sample number 1. We've got 4.3 grams of oxygen and 3.2 grams of carbon. I forgot the G. There it is. So 4.3 divided by 3.2 equals, and with 2 sig figs, that's going to be 1.3. So that's 1.3 to 1 is the ratio. Then the other one is 7.5 grams of oxygen to 5.6 grams of carbon. That's not carbon. 7.5 divided by 5.6 equals, and that is also 1.3 to 1. The ratio of the masses is the same. Any questions? Yes?
Does it always have to be presented in a ratio like that? Or could we take the oxygen and the carbon, add them together, and then divide either the oxygen and the carbon from the total to get a percentage?
You could find a percentage. Yes, you could. The percentage would be the same each time. In fact, let's do that. So if this has 4.3 grams of oxygen and 3.2 grams of carbon, then what's the mass of the whole sample?
7.5.
Yeah, 7.5. We add those two together, and so the mass of the whole sample is 7.5 grams of the carbon monoxide. And then let's say we're going to find the percent oxygen. So that'd be the mass of the oxygen divided by the mass of the whole thing times 100. Because percent is the part over the whole times 100. So 4.3 divided by 7.5 equals, that comes out to 57%. It's 57% oxygen. And then we can do the same thing with the other one, 7.5 plus 5.6 is 13.1. So the whole thing weighed 13.1 grams. The oxygen was 7.5 grams. And multiplied by 100. 7.5 divided by 13.1 equals, times 100, 57%. So yes, that definitely works too. And some of these things, you know, some people look at that first one and say, oh, well, that's much easier. And other people say, that was really confusing. This makes sense to me. It's just how you think about things. But the idea is exactly the same. Any other questions?